and then do a t-test. If beta 3 is statistically significant, then we have endogeneity. And at least there's evidence of endogeneity or simultaneity. If it's not statistically significant, then we don't have endogeneity. All right. So let's see. So X1 is endogenous. Construct an instrument. Z is that thing. So this is called instrumental variable regression. And this is how we're going to solve our endogeneity / identification / two-way causality. We're going to use something called instrumental variable regression. And these are the conditions for an instrument. Our instrument needs to be uncorrelated with the error term U. What does that mean? It doesn't belong in our primary equation of interest. So whatever our instrument is, remember it's got to shift. In this case, it's got to be something that belongs in the supply curve, but doesn't belong in the demand curve, so that we can shift the supply curve and identify the demand curve. So that's what that means. It's just the technical. So it's uncorrelated with the error term, meaning it doesn't belong in our demand equation. Because remember, the error term is supposed to include everything that affects demand, or everything, in this case, everything that affects demand, but that's not included in the regression. Measurement error, for whatever reasons, we didn't include it in the regression. So it's got to be something that doesn't even belong theoretically in our primary regression equation of interest. This is called the orthogonality assumption. And it needs to be highly correlated with our problem variable x1, which makes sense here, right? It belongs in the supply equation, but it doesn't belong in the demand equation. All right, test the validity of the instrument. Well, we can't observe the error term, so we really can't test for the exogeneity assumption. What we do is just kind of justify it theoretically. Does it belong in the demand equation? Nope. Is it correlated with price? Sure. Then we can use it as an instrument. We can test whether the problem variable and the instrument are correlated by kind of looking at a regression between the two. And making sure that they're highly correlated. So the operative word here is highly correlated. All right, so what do we get? Instrumental variable regression. It doesn't mean we actually substitute one for the other. It means essentially the instrument is, so here's the equation for our coefficients for OLS. It's kind of your mathematical equation. Essentially what they do, what instrumental variable regression does is substitute the instrument, or use the instrument in the mathematical equation here. We don't need to know how to do the math. Stata will do it for us. But it's almost like it's taking its place in the mathematics so that we can control for the fact that it's not strictly exogenous. One method of instrumental variable regression is called two-stage least squares. Two-stage least squares occurs in two stages. So the first stage is that we construct the instrument. So we take the endogenous variable and we regress it against all the other exogenous variables, including our instrument here. So this is similar to that first step of the Hausman test, which we call the reduced form equation. We're going to save the predicted value for this. So predict hat. So we're going to have x1 hat. And we're going to use x1 hat in our regression in instead of x1. So we use our instrument in place of it there, and that'll give us our more accurate measure of x1 on y. All right, so let's do a couple examples. Back to supply and demand. Neither supply and demand are identified. We can add income to the demand equation, the price of inputs to the supply equation. If we want to identify the demand curve, we're going to use input prices. So remember, we have those two conditions for an instrument. Our input price is correlated with price, probably, right? So if we think about this in just we regress price of anything equals gamma 0 plus gamma 1 price of an input plus EI. All right, as the price of inputs go up, the price of the product's going to go up. Whether it's computers, whether it's cameras, whether it's whatever. Price of inputs are going to be correlated with our product price. All right. Does the price of inputs belong in our demand equation? No. It belongs in the supply equation, but it doesn't belong in the demand equation. So it's orthogonal to our demand equation. So it satisfies our two conditions. We only have two conditions. It satisfies our two conditions for a valid instrument. If we were going to identify the supply curve, we can use income. Is income correlated with price? Yeah, through the demand curve, we know that as income increases, it's going to affect price. Is income correlated? Does income belong in the supply curve? No, it belongs in the demand curve. So income is probably correlated with price, and it's not, and it doesn't belong in the supply curve. So we can use that to identify the supply function. Houseman test. All right. So let's, what are we doing here? So our reduced form equation is, remember, the problem variable, which is price, and we regress it against all of the exogenous variables, which in this case are just going to be income and price of inputs. What do we do next? We save the residual, squiggly hat. We put the residual into our demand curve, which is our curve of interest, if you're concerned about interest, about demand. And then we test to see if it's statistically significant. If we want to identify the supply curve, you throw it into the supply curve to see if it's statistically significant. If it's statistically significant, then we have an endogeneity problem. And the reasoning for that, the reasoning behind the Houseman test is actually pretty simple. Remember, the error term is supposed to be a completely random variable. It's supposed to contain all the stuff that we can't control for, and on average it's 0, but it's a completely random variable that's unpredictable. So the error is supposed to have no predictive power. The error term contains no information valuable to us. When we put that error in there, if it's statistically different from 0, that means there's some information contained in that error when there shouldn't be. So what we're saying is that that error term doesn't satisfy our conditions for a valid error term. So that's our measure of endogeneity. That's the logic behind the Houseman test. We just do a t-test and look for the coefficients. T-test on beta 3 and for demand, and a t-test on alpha 3 for supply, to see if those are statistically significant. sales and advertising. We already know this, we've got two-way causality. We need to find an instrument. So we constructed this thing called a advertising function. Advertising depends on sales, we know that by the optimization rule, but it's also going to depend on the price of advertising. Does the price of advertising satisfy our two conditions for a valid instrument? Is it correlated with pricing? Obviously. If the price of advertising increases, we're going to buy less. If it decreases, we're going to buy more. Does the price of advertising belong in our sales function? No. At least not directly. It belongs in there through its effect on advertising. So we satisfy our two conditions for a valid instrument. We're going to Houseman test. So here's our two equations. We're going to take our problem variable, because remember what we want to do is measure the effect of advertising on sales. So we want a accurate estimate of beta 1. Beta 1 tells us the effect of advertising on sales. But because of the endogeneity, we know that it's going to be biased. So we're going to check that bias by doing the Houseman test. So here's our problem variable. We're going to run it against advertising. We're going to run that regression, and we're going to save the error term, squiggly hat. We're going to put that error term, squiggly hat, into our primary equation, our sales function, here. And then we're just going to do a t-test. If beta 3 is statistically significant, we got a problem with endogeneity. If it's not, then we don't. Starting to make sense? This is kind of out there stuff. But like I said, it's almost, well, it's endemic to what we do. And it's, I can tell you that a lot of people that have gone into the field of analytics, this is one of the first interview questions you're going to get. Do you see any problems with endogeneity? If so, how would you correct it? And you just have to be able to answer this stuff. Like I said, it's not a matter of if, it's a matter of how do you correct for it. If you want to read probably the best paper on this, that's the best one I could find. Estimated demand for wine using instrumental variable techniques. This was interesting. Well, it was fascinating because I'm estimating in the field of wine analytics. Right, so we're estimating demand for wine. We know that price is endogenous, and most people want, most firms, the wine industry wants a good estimate of beta 1. How sensitive are consumers to price changes? So we want a nice estimate of the demand for wine. What is the most obvious instrument for identifying the demand for wine? What do we use in any other demand curve? The other demand curves. We used the we use the price of inputs, right? Something in the supply curve that's not in the demand curve. So what would be the obvious input, price of input into the supply of wine? What's the number one thing that goes into wine?
Grapes.
Grapes, yeah. So you would think the obvious one would be alpha 1, alpha 2, price of grapes. Now, the price of grapes, so if we looked at this, price equals gamma 0 plus gamma 1 price of grapes. price of wine correlated with the price of grapes? When the price of grapes go up, what happens to the price of wine? It should go up, right? That's not many, sorry. Numerics. So we have two conditions for a valid instrument. The second one is the orthogonality or the exclusion principle. Does the price of grapes belong in our demand equation? No. So we satisfy both of these. Here's the problem, however. And this is why this was kind of a breakthrough paper. Remember that this makes perfect sense. And it's what people have been trying for hundreds of years, or at least a couple of years, in the wine industry, in the field of wine analytics. The problem is, if you ever looked at a scatter diagram, that was actually pretty weird looking handwriting. If you ever look at a correlation between the price of wine and the price of grapes, it looked like that. It's a shotgun blast. The problem with using the price of grapes as an instrument was satisfying. So theoretically, this made perfect sense, but practically speaking, in action, you get a correlation of 0. There appears to be no correlation between the price of wine and grapes. So all the estimates of the demand for wine are going to suffer from this endogeneity problem. Nobody was ever comfortable with this until 2008. It all changed. The world changed as we know it. So I'm like, oh, yeah, there's a lot of smart people that took a look at this. Let me take a look. So I looked at it, and kind of the solution was kind of obvious. This was the price. So we get some scan data, we get some crush reports. This was the price of all wine scattered up against the price of all grapes. What is the one thing that characterizes the wine industry? What would you say the one thing that characterizes it? The entire wine industry. If someone mentions to you wine, what do you think of? How would you describe the wine, the market for wine? Yeah, but it's kind of obvious when you think about it. And again, you're not the only one that's been stumped by it. Everyone before 2008 it was stumped by it also. Think about this. If we talked about, what are you talking about? Are you talking about two-buck chuck? Are you talking about Opus 1?
Range.
Yeah, segmentation. One of the things, the primary thing you think about the wine industry is it's highly segmented by price point. So what we have is, this is the price of all grapes, this is the price of all wine. And there is no correlation between them. But if you looked at wines by segment, and that's all I did, is I took wines and I said, I'm going to look at it by varietal, and I'm going to look at it by price point. So I'm going to break up the data. Instead of looking at all wine and all grapes, I'm going to look at the price of Cabernet Sauvignon and the price of grapes in Cabernet Sauvignon grapes. And what it turns out to be is that this isn't a shotgun blast. This was a demand curve, this was a demand curve, and this was a demand curve. You just had to figure out that all those demand curves into one data set is going to look like a shotgun blast. And I found this rule, actually I actually met the guy. It's called, it's called what's his name? He's a grape grower in Napa called something Hoffer. Beckstoffer. Beckstoffer's rule. It's the 100 the 100 price rule. So for a bottle of wine, for a $10 bottle of wine, the price of grapes were 100 times that. It would cost about $1,000 a ton. Does that sound about right?
Yeah, we were actually covering in the global wine business class, and I can't remember it. It was like, yeah, one bottle should be,
The bottle price rule.
yeah, like X amount of,
Yeah, and it's called the Beckstoffer rule.
yeah.
And I actually did some work for Beckstoffer at one time. And I came across the Beckstoffer rule. So I used the Beckstoffer rule to say for wines within this price range and this price range, I'm going to multiply that times 100 and look at grapes in those, 100 times that times 100 times that for that specific varietal. So I looked at, and what I found was I got these nice correlations. So what I did was I used the Beckstoffer rule, segmented the wine by varietal and price, and I came up with extremely strong instruments of correlation between the price of grapes and price of wine. Hence, I came up with, I used instrumental variable regression, breaking the data down, and I was able to get much more accurate estimates of our price coefficients. So that was the key. The key was recognizing that the wine industry is highly segmented, and you can't compare, if someone asks you if you like cars, minivan or Ferrari, they're both cars. There's a big difference between 2-buck chuck and Opus One. So that was the contribution to this paper. Pretty smart. I mean, pretty simple. Yes, it was smart, but it's also simple. All right, and by the way, this paper is being taught in other graduate schools to teach instrumental variable regression. Ryan Huffman is now the director of digital analytics for VSP, Vision Service Provider. Anybody have VSP insurance? Yeah. They're the biggest, I think they're the biggest insurance insurer in the United States. So he's doing extremely well. He's got to be pulling down maybe 250 readings. He's doing all right. He's probably not much older than you guys. So he graduated so he's 2008. So he's a couple years out of school. This is another one of my favorite ones, but let's skip this one for a second. This is a weird one. I'll just show you the headlights for it. This paper is trying to predict the number of affairs among women in the Kisumu County in Kenya, around Lake Victoria. And it turns out that women who were married to men with larger penises had more affairs. I'm not making this up, this is an academic paper.
Did you do this one?
No, I didn't write this one.
Oh.
This was those guys. I just came across it and I just started reading. I'm like, this is the most bizarre. Believe me, I don't even know how I even started reading the paper with that title on it, because it just, I'm like, okay, they're predicting extramarital affairs, so that probably caught my eye. I'm just kind of reading it, and then okay. So one of their conclusions was women who were married to men with larger penises tended to have more affairs. So I'm thinking, okay, that makes sense. All right, but that doesn't make sense. What they could be doing is
they go around measuring everyone?
yeah.
So
It's a long fight.
Well, it's
so weird.
you got to read the paper. I'm going to put it on my website.
Or research students.
So what they're saying is that penis size of the husband causes women to have more affairs. So that's the direction of the causality. What I'm saying is there might be some endogeneity here. And that it could be that women likely to have more affairs prefer men with larger penises. So that, yes, that one may be true, but it's probably also true that the other one, it could be true that it's working the other way. And if you read the paper, they make no mention of kind of endogeneity and controlling for it and coming up with an instrument and blah, blah, blah. I don't know if they have that much statistics, but this tells you how important kind of this stuff is, that professional researchers aren't going to have that much statistics. Okay,
Truck size does not highly correlate, or is highly correlated with the
we can do it to control for limited variable bias, ability bias. Let's get on.
bigger the tech.
All right. But here's one of the other ones that I think, and I have this in a presentation, I think I showed you guys the presentation. And this has to do with, again, just kind of two-way causality. Yeah, but we know the two-way causality happens here. So the one that I think I showed you, I don't know if I was done with the big photo, but it was sales equals beta 0 plus beta 1, and this was FBL. And it was binary. So FBL stands for Facebook likes. 1, if you like on Facebook, 0, if not. And what they're trying to show is that, what they did show is that if you like someone on Facebook, right, liking someone on Facebook causes you to buy them. And I think the result was something like, if you like them on Facebook, you spent $200 more per year, something like that, times, I don't know, 10 million likes, so something like 200 million, some ridiculous amount of incremental value. Did I tell you about this? Yeah. And yeah, what I said is, look, it's probably that's maybe true. What I know, I'm absolutely certain of, is that the products I like the most, or the products I buy the most, I'm probably going to like on Facebook. So this one I'm absolutely certain of, and that's not what you're measuring, right? When we run a regression, our implication is that the causality is going this way. So this maybe, probably, maybe the interaction and all that stuff. Remember, it's just a form of interaction just on the internet. But there's probably going to be a return to that. But this one I'm certain of. So the problem with this is the endogeneity problem. There's two-way causality. You really have to find an instrument for whether or not you like something, a specific product on Facebook. So that's perhaps one of my favorite examples. All right, so let's see how we do this. Limited variable bias, ability bias. Well, this one's interesting just for the instrument they use. Here's the data set we have. Actually, let's just do it in data. Is it still a blowout, I assume? Did they catch up?
I don't know. Who has it? Somebody's got it. Come on.
The game?
Yeah.
I have the game.
It's over.
Oh, you got. Who won?
Kansas City.
Oh, okay.
So it's over. Kansas City won that. This game, I've been there for a while. They're just beating them.
They were awful. But it's not their fault. That's their fault.
Oh, dude, it's called.
All right, so we got a nice little data set here. It's a made-up data set, but it's a really good learning data set. Q is the amount of pizza sold per month. P is the price of pizza in that month. Comp is the price of a competitor's pizza. Wage is the wage of pizza makers. And cheese is the price of cheese. So let's assume we're going to estimate a demand curve. So if we're going to estimate a demand curve, we're going to include those things that belong in demand. So we want quantity as a function of price. And does wage belong in the demand function? Nope. Does the price of cheese belong in the demand function? Nope. But the price of competitors does. So we can do that. All right. So here's our estimate of our demand curve. So we've included the things that we have data on. And we're getting a negative coefficient for price, which is good. We're getting a positive coefficient on our competitor price, which is good also, which means that everything makes sense. Everything's at least consistent with the law of demand and with what economic theory would tell us about, right? If the price of the competitors goes up, they're going to buy less of the competitors and more of yours, so that's our positive coefficient, and it's statistically significant. Yay for us. But we know that estimating demand inherently comes with an endogeneity problem. It's endemic to every demand curve that we can get. So what we need to do is test it for endogeneity, and then either fix it somehow using instrumental variable regression. So we're going to run our Houseman test. So essentially we got, let's see, we got a demand curve. Beta 0 plus beta 1 price plus beta 2. And this is also a price, but it's price of a competitor plus our error term. And we have a supply curve equals alpha 0 plus alpha 1 price of pizza plus alpha 2, what is it, wage of pizza workers plus alpha 3 price of cheese. So the Houseman test was take the problem variable, and what's the problem variable again?